Welcome! We are the MIT Design Build Fly team, and this is our video submission for the 2020 to 2021 DBF competition. Our plane is Mary, aka the majestic agent of roll and yaw. The team worked completely remotely due to the COVID-19 pandemic and made the best of a crazy year. This is our design.
The plane and sensor models and renders were made on SolidWorks, and the dimensions of the plane are as follows. The general airframe has a length of 59.54 inches, a span of 60 inches, and a total height of 15 inches. We used a custom fuselage with a length of 11.81 inches, a max width of 4.92 inches, and a max height of 7.54 inches. For the wing, we used a combination of an E64 and an SD7032 airfoil. The chord is 16.37 inches and the span is 60 inches. The horizontal tail has a chord of 7.87 inches and a span of 20 inches. The vertical tail has a chord of 4.53 inches and a span of 9.07 inches. Both tails use a NACA 0012 airfoil as the shape. The sensor has a diameter of 1 inch and a length of 11.81 inches. Overall dimensions aside, the CAD was done on SolidWorks, with the work being split up among several members of the team. Each person focused on CADing specific parts, and in the end, the work of all the members was compiled to create the final product.
On this slide, we can observe the gross weight of each major component on our plane. So besides the fuselage, which weighs approximately 3 kilograms, our plane weighs a total of 6 kilograms without a payload, and then our payload, which is about the same weight as our fuselage, brings the total weight of our plane to 11.4 kilograms, which is its heaviest for mission 2.
Our control architecture is coupled with the aircraft configuration you see here, with a high wing, a conventional tail, and equal thrust to twin motors. Our choice of control surfaces is fairly standard, with twin ailerons for banking, centered on our motors, a small rudder for yaw corrections, and a wide elevator for pitch.
Our propulsion system consists of two 6-cell LiPo batteries in parallel, a Castle ESC, and two Cobra C motors, each with their own 14 by 8.5 propeller. A principal feature of our design was the decision to use two motors. We did this in order to maximize payload in mission 2 and increase speed for all missions. Since we decided on using two motors, LiPos were the optimal battery choice given their high specific energy. In all missions, we connected the batteries in parallel and they are stored in a compartment at the front of the fuselage. The current running through the motor is around 70 amps, so we chose an 80 amp Castle ESC. Based on the power requirements for our speed goals, we selected candidate motors that would provide the best thrust for the lowest mass and lowest price. While unable to perform propeller tests, we chose our propellers based on available data charts. We mounted the motors on either side of the plane, secured to the leading edge of the wing by custom motor mounts. Power wires extend from the battery compartment and route along the fuselage and wings to ESCs, which were mounted just behind the motors under the wing.
The aero team focused on 4 assemblies: the wing, the fuselage, the empennage, and the sensor body. Here are the 2 wing configurations we considered. Given the pros and cons listed in the chart, we ultimately chose a high wing because of the listed benefits and easier sensor access and deployment. Displayed are the 2 configurations we considered for the fuselage. We chose the pod and tail boom because of ease of manufacturing, simplified CG calculations, and efficient tail volume allocation. For the empennage, here are the 3 configurations we considered. Given the benefits and drawbacks on the chart, we chose a conventional tail, emphasizing ease of manufacturing. Displayed here are the designs we considered for sensor bodies. The flying body was our first choice, since it was optimally designed, but since it didn't fit the competition parameters, the cylindrical body was our next best choice.
The goal of the sensor container is to protect the sensor. Here are the contenders. The first thing we considered is reliability, which brought everyone ahead of the spring walls. Next, we considered complexity, which brought the hammock back down. And finally, effectiveness, which made the padded container and the wrapped sensor the winners.
But who cares? Just make the sensor durable.
The goal of the sensor mechanism is to deploy and retrieve the sensor. 2 simple machines sound like a win-win, but it could be difficult to get right. It would also be fun to build a conveyor belt, but that might require an extra servo. Or should I just keep it simple? Maybe a conveyor system that's not motorized? Nah, let's just keep it simple.
Using our code simulations, we made predictions as to how the plane would perform for each mission. For the first mission, simply flying the plane, we predicted we'd get a full score. For mission 2, although we optimized the score using 8 containers and taking 200 seconds, we determined that taking 165 seconds with 6 containers along with our sensor was a more realistic approximation. We then calculated our predicted score based off of this 6 container payload, assuming that the best team would have a near perfect run. For mission 3, we determined the optimized run would be 12 laps, carrying a 1 meter length sensor with a mass of 3.5 kilograms. However, we realistically believe our plane would do 11 laps with a 0.3 meter long sensor weighing 0.81 kilograms in the allotted time. These parameters would give us a score of 2.064, assuming the best team had a perfectly optimized run. For the ground mission, we optimized our time at 44 seconds, but predicted we'd take around 123 seconds in reality. Assuming the best team got the perfectly optimized score, we get a score of 0.358. Thus, our estimated total score would be 5.331, the sum of all our scores for the individual missions.
We ran tests on the sensor design in order to evaluate its stability and drag characteristics. Here, the test stand is seen along with the prototype sensor. This sensor was 3D printed with ballast added to make it our expected weight. In the absence of a wind tunnel, the test stand was built to be held outside of an automobile where data could be collected using a load cell and an Arduino. To perform the sensor testing, the sensor and its stand were held outside the window of a car whose speed was manually recorded. Tests were done from 5 to 30 miles per hour in increments of 5 miles per hour, and here you can see the sensor testing at that final point of 30 miles per hour. Here, we can look at the different tests, their loads in grams, the average drag produced by the sensor in newtons, and the coefficient of drag calculated with respect to our wing's planform area. At the aircraft's Mission 3 target airspeed of 51 miles per hour, the sensor had a CD of 0.044.
Our aircraft is optimized for Mission 2, which makes the maximum mass of the aircraft is around 11 kilograms. To make sure the aircraft can withstand that heavy weight in various maneuvers, we build and validate our structural frame with a 3-point bending test. The frame consists of 2 wing spar, booms, 4 fuselage spar, they're all made out of carbon fiber too, and 4 fuselage plywood bulkheads. On the wing boom fuselage joints are wrapped with carbon fiber towel. In the 3-point bending test, we started with 12 kg and gradually add 2 kg weight onto the expected center of mass point. We then observed the bending effect and recorded the result from 12 kg to 22 kg load. Here's the 12 kg, 14, 16, 18, 20, and 22. The result shows that our structure could bear the load in 2G condition with reasonable bending displacements.
We tested the motor using the RC Benchmark 800 testing stand. The purpose of this testing was to ensure the performance of the motor was as we had calculated. We increased the ESC signal and collected data on voltage, thrust, power, acceleration, and torque. We reached a maximum thrust of 3.76 kilograms force, and we calculated that this thrust was sufficient to reach the desired speed. We changed the ESC in a stepwise incremental manner because increasing the ESC signal for too long caused a burst current warning, so we had to make sure the current went down before the next increase. This was also why we could not get to the expected full thrust of 4 to 5 kilograms force, as we were not able to reach full throttle. After reaching the maximum, the battery power decreased, causing a decrease in thrust and power.
Similarly, we created different prototypes in order to determine how to best protect the sensor during the drop test. Here, we used 3D printing to create 2 different types of container shells, and essentially performed an egg drop test using various types of internal padding. We utilized bubble wrap, cotton balls, foam, and cotton pads to test protectiveness. After testing, we concluded that lining a shell that opened lengthwise with bubble wrap gave us the most effective container design.
And that wraps up our video. Thank you for taking the time to watch the whole thing, and now we have some pictures of the plane. Enjoy.